His presentation is about the anatomy of a high-penetration wind diesel power systems. So Steve is president and founder of Sustainable Automation. He holds a Bachelor's of Science in Mechanical Engineering from Brown University, an MS in Environmental and Applied Fluid Dynamics from the Von Karman Institute for Fluid Dynamics, and a Master's of Engineering in Mechanical Engineering from UC Berkeley. His experience in the wind energy industry spans more than 20 years, having begun his career in 1982 working for U.S. Wind Power Incorporated as a field test engineer on the very first California wind farm in Altamont Pass. From 1994 to 2002, he worked at the National Wind Technology Center at the National Renewable Energy Lab, where he led NREL's program in wind diesel hybrid system research and development. He was a principal designer of the high-penetration wind diesel power system implemented in the Arctic village of Wales, Alaska. So Steve also has come quite a long way to be up here in Alaska, and we're really thankful to have his expertise in this session. So thank you, Steve.
Thank you for that introduction, Kat. So she already gave you the title, and she already gave you my bio. So we'll just move right along past that. Just a few words on my company. As Kat mentioned, we were founded in 2002. We provide a variety of services. In the early years, it was a lot of consulting, mostly system feasibility studies, system integration engineering, trying to educate and build a market, educate people as to what was possible. That's an ongoing process, and that's kind of about what we're here today talking about. But increasingly, there is a market, and increasingly we're a manufacturer of such systems. We have a facility in Boulder, Colorado, a combination of office and lab space where we do our manufacturing and R&D on these systems. Some of the products which I'll be speaking about that we design and build are hybrid system supervisory controllers, secondary load controllers, synchronous condensers, and power electronic power converters. And wind diesel is our primary application, but that can be applied not only to village power, but also remote industrial sites, resort communities. There's islands in the Pacific and the Caribbean that are wholly owned by resorts. Here's just a shot of our lab and test facility. Some of the components we have installed there. As I mentioned, it's difficult what we're trying to do is create a test environment that, even though it's at a relatively small scale, it's representative of the systems that we encounter in the field. It's a little bit difficult to have a working wind turbine on site, so we have a wind turbine simulator that's a induction generator driven by a torque-controlled variable speed drive that allows us to feed in computer files of either power time series or wind speed time series data, which will then do the appropriate conversion and allow that machine to simulate what the actual fluctuating turbine output would be. We have a generator set, a secondary load controller, synchronous condenser, recently installed a battery inverter system. And although most of our applications are off-grid, it's useful to be able to interconnect with the grid, both for testing individual components, but also to, on occasion, simulate systems that actually would be grid-tied, which might be the case in, say, an industrial system that might want the option to disconnect from the grid at times. So I've titled, there's the phrase high penetration in the title. Russell just talked about that briefly. I have somewhat of a different definition, although we both speak in terms of instantaneous wind penetration. He didn't get how you could have over 100%. Well, by my definition, which is the instantaneous renewable output, in this case wind, divided by the instantaneous load, well, it's easy to see that you can have quite a bit more wind power output at any given moment than you have load, which would, so that means, by my definition, that you can have wind penetrations well in excess of 100%. at any given time. Part of my definition also, and this is not universal, it's just the way I think about it, is that a high penetration wind diesel system is designed to go diesel off. It's capable of operating with the diesels completely shut down, and in fact the goal is to do that as much of the time as possible. That's not the only way to do wind diesel, but it's sort of what my company is about. It's more difficult, it's more challenging, but the rewards are obviously greater in terms of fuel savings and reduced operating cost on your diesel power plant. You'll hear a lot about low load diesel operation this week. One issue around that is, yes, it's feasible, but much of the operating cost of a diesel, or certainly much of the maintenance cost, is a function of run hours, not load levels. So if that machine is online accumulating hours, you still have to do the oil changes. You still have to do the major overhauls at a certain set number of hours. So we like to keep them shut down. We're also anticipating the day where we have improved energy storage technology. The price comes down, longer energy storage becomes feasible, and then we'll try to do diesel, no diesel systems, or complete 100% renewable systems. That's a ways off, but that's a long-term goal. So I just wanted to put high penetration in context so you know what I'm talking about. Sure, Brian?
I don't want to wade too far into it, but I mean, from the Alaska context also, I think we're talking about fuel switching, where, I mean, if the main focus is reducing diesel fuel consumption in a village, most of the diesel fuel consumption is actually for heating, not for electricity. So if you can have over 100% of your load, electrical load met, you can theoretically be using some of that wind generation for displacing diesel heating fuel. And so
absolutely,
you get over 100%, that's maybe another way of looking at it, as you have opportunities to fuel switch.
Exactly. So what I'm trying to do in this presentation is narrow the focus a bit and hopefully look at each of the major components that go into a wind diesel system and convey an understanding of what its specific function is and how does it, what its operating principle is and what role it plays in the big picture. There's a lot of confusion when you get into these balance of system components. I don't think people understand them very well, and as Russell pointed out, a confused mind tends to say no. So I'd like to get people to better understand what all this other stuff is for, and particularly address the question of, why do we need it? And you get a lot of sticker shock when people first are contemplating going the wind diesel route, because they initially think, well, I've got the diesel power plant, I just need to add the wind turbines, right? And no, it's not that simple. And what the shocking part is when they find out that the balance of system on a small system like sort of Wales or Kokonok can be, the balance of system can cost just as much as the installed cost of the wind turbine. So, and people step back and say, whoa, when they hear that. But fortunately, as the systems scale up, that ratio goes down. But it adds considerable capital cost to the system to be able to go high penetration. But the economic benefits are ultimately there. So what does a power system have to do? And there'll be some overlap between my presentation and Russell's, and that was inevitable. Last night was the first opportunity we had to sit down and chat about what we were going to talk about, and we decided, well, okay, it's kind of late in the game to avoid that, but in any case, you're going to be hearing certain things from a very different perspective. And the perspective I'm taking here is really the task of the power system designer. What does a power system have to do? Well, fundamentally, it has to, and this is what a utility's job is to regulate voltage and frequency. If wherever you plug in that appliance or connect that machine, you've got a well-regulated voltage and frequency. The utility's done its job. The rest is just billing. So basically, you've got your voltage waveform. Frequency, the period of those cycles, you want that to stay constant. You want a constant 60 hertz. And the amplitude of the voltage, you want to be fixed at whatever it's supposed to be, whether it's 480 volt system or 600 volt system, whatever. So that's what the power system has to do, and that's kind of the problem that I want to address in this presentation. You can boil this down as a problem of balancing two things, real power and reactive power. Frequency regulation is essentially a problem of making sure on an instantaneous basis all the real power sources equal all the real power sinks. If you don't do that, if there's an imbalance between the sources and sinks, the system will speed up, or it will slow down if you're taking out more power than you're putting in. And this, you can think of all the rotating machines, whether they be in the generators, like the diesel generators or the wind turbines, or the loads, like pumps, washing machine motors, whatever. They all have spinning mass, they all have inertia. So the imbalance in energy gets stored as, the stored energy of all those things will increase, and you'll have a corresponding increase in system frequency. So the problem of frequency regulation is a problem of balancing real power at all times. Similarly, the problem of voltage regulation is a question of balancing reactive power. There's a subtle difference here, is there's no reactive power can't be stored. So it turns out that whatever you do, the supply of reactive power will necessarily equal the dissipation of reactive power at all times. The problem is that you need to provide the reactive power which will hold the voltage at a certain level. If there's too little reactive power compared to what's demanded by the system, the voltage will sag. Similarly, if there's too much, the voltage will rise. So that's the problem. At all times, we must maintain a balance of real and reactive power. And like the old saying goes, if you're not part of the problem, if you're not part of the solution, you're part of the problem. And so one useful way to look at this is to look at each power system component and classify them. Are they part of the problem or are they part of the solution? I'm going to just switch to if you can see that. This is the one-line diagram for the power system at Kokonuk, which some of you may be visiting on Saturday. It's a existing diesel power plant consisting of 4 generators, a synchronous condenser, a secondary load controller, and a battery inverter system. And then out on the grid, there are, I've shown more here, but there are actually two 95 kilowatt wind turbines, and then you've got the village load. So which of these things are part of the problem? In other words, they don't help you control frequency and voltage, and which do? So the load is actually the problem because you have no control over it. The consumers, the load is just the aggregate behavior of all the consumers that are turning things on and off. And they tend to do that when it's convenient for them, not when it's convenient for the power system. So they are an imbalance that has to be dealt with. Wind turbines, similarly, we're here talking about how much we want to introduce wind power. Well, from the power system designer point of view, wind turbines are part of the problem, and that may offend a wind turbine supplier, but it's actually, as you're all well aware, renewables are intermittent. This is a graph of superimposed solar insolation and wind speed. The units or the particular location isn't important. It just conveys the fact that renewables are highly intermittent. The solar resource is inherently more predictable than the wind, but with weather patterns and passing clouds, you can have extreme ramp rates in solar power output as well. So you've got a uncontrolled intermittent resource that's putting power into the grid. So that is a problem to be dealt with from the point of view of a regulated power system. And you can understand why in the early days, especially, utilities were very loath to introduce renewables to their grids because they didn't help solve their problem. They just exacerbated it. Wind turbines, they don't contribute to voltage or frequency control. They require, again, as Russell pointed out, they require a fairly well-regulated grid to connect to. They're designed, most of these machines that we deal with in the village power projects were not designed for wind diesel applications. They're designed to be connected to the grid, so that's what they expect to see, a well-regulated frequency and voltage. And if you deviate from a fairly narrow band of frequency and voltage, they won't operate. There's a caveat that I should mention here. Is some, especially more modern wind turbines with full power conversion in the generator itself, in other words, a power electronic converter that's the interface between the machine and the grid, they have the ability to control their reactive power load. Generally speaking, especially in the smaller size range, at best they avoid contributing to the voltage control problem by not introducing additional reactive power load. They don't actively participate in controlling voltage. That's left to the other devices in the system. So what are the solutions? Well, obviously, the diesel generator is the tried and true solution. But there are these other things that I want to address as well. So let's just kind of walk through these, and feel free to raise your hand, ask a question at any time. We have time for that, so a little bit of discussion would be good. Diesel gensets, they do the job, and they do the complete job. They control voltage and frequency, and they do that by ensuring this balance in a real-time basis of real and reactive power. The real power is addressed with the throttle. There's a speed control on that genset. If the frequency starts to drop, they inject more fuel. It injects more real power into the system. I've been talking about real and reactive power. Does anyone not know what I'm talking about when I talk about real and reactive power? Basically, real power is that which does actual work. Reactive power is it's a mathematical concept, really. It's just the power that is the product of the voltage and the component of current that is out of phase, 90 degrees out of phase with the voltage. So it doesn't do anything useful, but it represents additional current flowing in the system that has to be provided, because real loads tend to have part of the load is a reactive power load. You never get, the only pure real power load is a resistor. Because in a resistor, the current is exactly in phase with the voltage, so it only consumes real power. So what are the pros and cons of a genset? Well, obviously there's the environmental issue, the fact that gensets burn very expensive fossil fuels, and we want to try to wean ourselves from those. In terms of from the power system designer perspective, they do quite a good job, but they can't, if you start putting a lot of renewables on a system, they're limited in their ability to regulate the frequency because they can't absorb power. I mean, and that's, again, there's exceptions to every rule, but a diesel genset can absorb a little bit of power before it loses its ability to control frequency. Maybe you can backdrive a diesel maybe 5 to 10% before it loses control. But it's generally not something you want to do because it operates very cold if you do that. It operates at very, very low load. And like I said, there's the wear and tear just associated with it operating at all. So what else can we do to solve the problem? Okay, one of the simpler devices is the secondary load controller. And that's kind of a generic term that can take many forms. There are many different types of secondary loads. Resistive heating and an electric boiler, water pumping, anything. A secondary load is a load that the system has control over as opposed to the primary load, which is the consumer load that you're trying to meet. So secondary load, like I said, can be resistive heating, it can be pumping, it can be ice making, water desalination. The one that's employed most often, especially in northern communities, is resistive heating because for two reasons. There's usually a demand for heat, so you can put that excess power to productive use. Also, it's the fastest response secondary load. Remember, you're trying to use this secondary load as a tool for power balancing, and you can, with solid state switches, you can achieve this very quickly and with very good resolution with a secondary load controller that's feeding an electric boiler, for instance. So what it does is, again, it helps you to maintain frequency control by absorbing any excess power. Just as the diesel can only supply power, the secondary load can only absorb it. So it's limited. It doesn't have the full range of control, and it only can exercise that control if you have excess power. Because if you no longer have excess power, then you have no margin of control to work with. So the secondary load does have limitations. What makes a good secondary load, as I said, is its ability to respond very quickly. And the electric boiler with rapidly switchable elements can do that. Our latest generation of secondary load control basically has about a 5 millisecond response time. So it's much faster than the diesel speed control, and it can actually, when you add it to the system, it can smooth out the frequency fluctuations so that the diesel essentially sees a pretty steady load, and it operates quite comfortably. You don't hear a lot of surging in frequency that you sometimes hear when you put a wind turbine in parallel with the diesel, when the wind turbine starts to jerk the frequency around. Another thing that there have been different implementations over the years of secondary loads. Some led to very poor power quality. The phase control, power control, tends to have, people have gone away from that because that introduces a lot of harmonics and poor power quality on the grid. So one thing you want to look for in a secondary load controller is something that does not distort the waveform and doesn't introduce any harmonics that might propagate to either your diesels or to customer loads. Another thing about those types of power controllers, they tend to be noisy. Often you might want to implement a secondary load in close proximity to where you have the heat demand, if it's an electric boiler, for instance. And that might mean putting it in a customer facility. So you don't want something that is going to be sitting there generating a lot of electrical noise. And so with our approach, using solid-state switching and no waveform distortion, they're absolutely quiet. You never know it was there, so you can stick it, in the utility room of a school, for instance, and no one's going to notice it. Synchronous condensers we touched on a little bit earlier. Now we're getting to the other power balance that needs to be achieved, and that is the reactive power balance. A synchronous condenser is essentially a synchronous machine just like you would find on a generator set without the engine, without the prime mover. You can see in that picture there's well, actually you can't see there's a small pony motor that brings it up to speed so that it can synchronize with the grid. But as soon as it's synchronized, the pony motor shuts off, and it's just spinning on the grid, and it's got a voltage regulator connected to the synchronous machine, just like any genset would. And you control the supply or absorption of reactive power by biasing the voltage regulator set point, just like you do on a standard diesel genset. Some of the pros and cons of this type of machine, they have the full span of control. They can deliver or absorb reactive power. The spinning mass of the, it is a rotating machine after all, so it has inertia. That inertia contributes to the system stiffness, both the voltage and the frequency stiffness. And as was pointed out earlier, that stored energy of that spinning mass can deliver a lot of fault current in the event that it needs to clear a fault in the system. And so if you have, frequently the diesel generators can do that, but if our goal is to shut them down, you need an alternate source of fault current to avoid the situations that Russell was talking about earlier, where you can have a sort of intermittent partial fault that's just wildly increasing the load on the system, but there's not enough oomph in the generators to clear that fault. Synchronous condensers are robust. It's difficult to hurt them. They're relatively inexpensive, especially as you scale up, because the controls required are essentially fixed cost, and the cost of the controls doesn't increase whether the rating is 100 kilowatts or really a kilovar, because you're really rating this in terms of its reactive power delivery, all the way up to 1 megavar or more. The cost of the controls stays relatively constant. Obviously, the size of the wire and the breakers and the contactors, that all goes up. But the controls themselves, which represent a considerable fraction of the cost on the smaller system, don't represent much cost on the larger system. One issue with synchronous condensers, because they are physical machines, they have bearings and friction, and both mechanical friction and windage. There are some losses associated with operating them. Fortunately, you don't have to operate them all the time, only when you have wind power. So generally, you can attribute, you're not using diesel power to run the synchronous condenser generally, because you would only run it when you have a significant amount of wind power that you need to provide additional system stabilization for. And lastly, we kind of marry these two functions with a grid-forming inverter and some form of energy storage. It doesn't have to be batteries. Batteries are what I'm showing here. This is actually the inverter and battery bank that's installed in Kakanock. And the idea here is that you have a system that just like a diesel genset, can perform both functions. It can balance the reactive power, controlling voltage, and balance the real power, controlling frequency. But it does the diesel one better in that it can deliver or absorb both real and reactive power. And that's called, and it can deliver real power while absorbing reactive power. That's called a four-quadrant power converter. So you've got real power, reactive power, either positive or negative in each. So you can see you have four possible combinations, whether you're delivering positive real power and positive reactive power, or positive of one form and negative of the other form. Diesels, diesel generators have been around a long time. The controls are deployed in, units of thousands. Any given type of diesel controller. There's many units out there. It's a standard product. They've been doing active load sharing and VAR sharing for a long time. Grid forming mode versus base loading, it's all well understood. The machines relatively gracefully switch back and forth between those two modes. So you can have 1 minute you can have a genset connected to the grid just in base load mode. This is a large utility grid I'm talking about. So it can't control voltage and frequency at that point because the grid would overwhelm it. But it can feed in power, maybe in a cogen situation or something like that. And if the utility goes down, it can immediately switch over to grid forming mode or voltage control mode, and it does that relatively gracefully. Inverters are a newer technology. There are voltage source inverters, there are current source inverters. There are relatively few that do both, and the challenge is the design becomes relatively complex when you're trying to provide a system that can operate in both modes. Either it's the master on the grid or it's assisting the diesels in a power control mode. And performing those transitions gracefully is still something that many people are working on. We're spending a lot of development effort in getting working out the kinks in that. So there's some complexity associated with power converters that you don't find in some of these other components. The inverter only works to the extent that it has energy storage connected to it. At least that's the only way that it can provide or absorb real power, because that power has to go somewhere, and it comes from or is absorbed by the energy storage that's connected on the back end. That can be a battery bank, that can be a flywheel, and as Russell, itemized this morning, there are many different types of storage and more coming on all the time. We're working on one project this year with a company that makes advanced lithium batteries, and they have some very, very exciting performance characteristics over traditional lead-acid batteries. But cost is the overriding issue pretty much in all forms of storage at this point. And lifetime, cycle life is limited, particularly with battery technology, less so with flywheels, and we're looking forward to more flywheels being available. I know there's some folks here from Beacon Power, and they have a very exciting product which offers the time scale of energy storage that is of interest in wind diesel systems. We tend to think of the sweet spot, at least for the larger systems, as being 15 to 20 minutes of storage. You heard Russell from Power Corp talk about their flywheel product in terms of seconds of storage, which is very useful in providing time to start the diesel, but not that useful in preventing the need to start the diesel. So our target and why we're currently using batteries for these systems is that we want to be able to ride through relatively short-term wind energy deficits without having to start the diesel. I mean, I'm talking about wind lulls that may last from 1 to 10 minutes without having the spinning reserve online to handle that, or without having to panic and start a diesel just because the wind dropped off. Because you could spend 2 days where your average wind power is 105 kilowatts with your load, your average load being 100 kilowatts. But every few minutes, the wind might drop down to 80 kilowatts or 90 kilowatts. But no, it's only going to last for a few minutes. So if you didn't have storage in such a system, you'd have to have spinning reserve on that whole time, burning fuel because you want to run the diesel at a certain minimum load, or accumulating wear on the diesel just because it's running and it's chewing up its interval between oil changes and overhauls. So the challenge, again, that was a little digression, but the challenge with the power conversion technologies, having it play well with others, in other words, parallel gracefully with diesel generators and other system components, and why do we need the other stuff? Why do we need a secondary load, and why do we need a synchronous condenser? That's a very good question. One answer, actually one that's not listed here, I'll start with that one. Why would you still need a secondary load? Well, if you're talking 15 minutes of energy storage and you're at 150% wind penetration, in other words, you have a 100 kilowatt load and your turbines are putting out 150 kilowatts. Well, you're going to run out of capacity in that energy storage pretty quick. So you still need some place to put excess power to avoid shutting down turbines. Most of these turbines have no mechanism for curtailing their power output, for limiting their power, other than shutting them off. And if you only have 2 turbines in your installation, say it's a small village, if you shut off a turbine, then you're losing half your power output, and you expose yourself to, what if that turbine has a failure? What if it drops offline? Well, you've just decreased your system reliability. You'd like to be able to keep your turbines online all the time and do something useful with all that energy that they're producing. That's how you're going to recoup your capital investment. Well, a secondary load that takes over once your battery is full, or your your flywheel is fully charged up to maximum speed, that allows you to recoup all that excess wind energy. Another reason is redundancy. We've got 3 things now, 3 solutions for frequency and voltage regulation. We've got the diesel generator. That's what it was designed to do. That's what it's been doing for years, all by itself. We've got the combination of the secondary load and synchronous condenser, which one of them controls frequency, one of them controls voltage. The 2 together can allow the system to operate in a fully regulated manner with the diesel shutdown, provided you have a margin of excess wind power. And then you have the inverter, which all by itself could control system voltage and frequency with the diesel shutdown. So the redundancy comes in between the inverter and the combination of the secondary load and synchronous condenser. Reliability to utility, reliability of power supply is everything. So if you're taking the extra step of installing the battery inverter system or whatever form of energy storage, you've already sunk a large amount of money into that system. that tends to be the most expensive component for a relatively modest, I mean, it's not cheap, but it's a very reasonable incremental cost. You can have the secondary load and synchronous condenser combination as well, and you need the secondary load anyway, as I said, to absorb excess power. That provides you a margin of extra reliability in case the inverter faults for some reason. The last point I want to make, though, is that having all three of those components allows you to optimize the size and provide an economic optimum, particularly in your power converter and energy storage system. If you if this green trace represents your wind power, and this blue trace represents your fluctuating load, the only power deficit that you really have to deal with are these periods where, and say 0 is there. So this is really, if you decide, well, I'm only going to operate diesel off when I have, on average, more wind power than I have load. The power deficits that you're dealing with are a fraction of the total load. And so you may not want to size the inverter to be able to meet the entire load. And if you start sizing it to meet this load, then it's going to have limited reactive power capacity as well. So it may not be able to support by itself the reactive power demand of the wind turbines and your customer load. However, if you can, so you might want to sort of reduce the size of the inverter just to what's really needed for most of the time, and then supplement that with the reactive power capability of the synchronous condenser. That might be overall economically more beneficial than just one big inverter and battery bank. And as I touched on before, the synchronous condenser inherently, because it's this big mass of copper and magnetic steel, it has the ability to deliver much more fault current than a typical inverter. So it provides additional benefits as well. So I got the, a few minutes ago, I got the 5-minute warning, which works out perfectly because that was my last slide. But we have some time for questions if there are any.
Steve,
Yeah.
can you...
Testing.
Okay. Steve, can you tell us what the typical loss for a battery bank is, both storing and retrieving energy, such as the one in Coconut?
Well, we don't have any data on the Coconut battery bank yet. The inverter in Coconut is not yet operational. It'll probably be the last thing that gets commissioned. However, from past experience, there's two types of, two measures of efficiency when you're talking about the round-trip efficiency of energy storage in a battery. One is the so-called coulombic efficiency, how many amp hours out do you get for how many amp hours you put in. And then there's the energy efficiency, which is somewhat less than that because the current that you get out is delivered at a somewhat lower voltage than the current. You can't get any more current or charge out of a battery than you put in. So even if you had 100% coulombic efficiency, the energy efficiency would be less than that because it's going to be delivered at a lower voltage. But what's really of interest is the energy efficiency. And if you operate your battery at intermediate states of charge, it's actually highly efficient, on the order of 90%. Yes, round-trip energy efficiency. Peter may have additional data on that, but I know he deals a lot with energy storage numbers. But if you, in something like a solar PV application, maybe where a battery is going through deep discharge cycles, it's like a remote cabin that's operating a solar system. You might get the battery fully charged during the day and kind of on float charge, where there's current trickling in, and then discharge it 60 or 80% overnight. If you measure the energy efficiency of that storage, it's going to be much less, because both at the top of the range and the bottom of the range, you lose a lot of energy just in the sort of electrochemical processes in the battery that not too many people understand. But I know that you might get 60 or 70% energy efficiency in a battery. But in the regime that we're operating under, it's an oversized battery. It's a lot of many cycles at very shallow depths of discharge, and we try to keep it in an intermediate state of charge where it operates efficiently. Long answer to it.
Thank you, that was good.
How many secondary load, or if you have a secondary load controller, does that control one load, or can it control multiple loads throughout the community, or do you have to have one secondary load controller for each thermal dump, if you will, or electric thermal dump?
Well, I have to distinguish between the sort of generic term and our product. Our product is specific to one electric boiler. Yeah, but you can have more than one of those. In fact, the operation would be coordinated by the supervisory controller, and I haven't even talked about that piece of the system, which is that supervisory control. But yeah, you can have multiple secondary loads in multiple locations. In the Wales system, we had one in the power plant, which was the fast response, high resolution secondary load, and then another one in the school, which was bigger load steps, slower response, but it basically allowed us to keep the plant secondary load within a comfortable control range, and any additional load would be sent to the school. Anyone else?
Thank you, Steve.
Thank you.